Hello everyone! In this video, we're going to discuss and solve problems involving other indeterminate forms. Say that we are given a rational fraction wherein the numerator is a function of x and the denominator is another function of x, we call it g of x, and if we're going to determine the limit of this rational fraction as x approaches a and the result turned out to be 0 over 0, now we know that this is an indeterminate form. Or if the result turned out to be infinity over infinity, this is another indeterminate form. Now, to solve for the limit of f of x over g of x as x approaches 0, we either manipulate f of x over g of x such that we can produce a certain value of the limit of this given function, or there is another method and it is called the L'Hopital's rule. The L'Hopital's rule is used when the limit of this rational fraction resulted in 0 over 0 or infinity over infinity. And to determine or to answer this one using the L'Hopital's rule, we're just going to simply determine f prime of x, or the derivative of f of x with respect to x, and the derivative of g of x with respect to x, so we're going to call it g prime of x, and then we're going to evaluate the limit of the resulting expression as x approaches a. So to illustrate this further, let's have examples, and we're going to evaluate the following. So for the first one, we're going to evaluate the limit of x plus tangent of x all over sine of 4x as x approaches 0. Now, if we're going to find f of 0 in this function, the result would be 0 over 0 because 0 plus tangent of 0, which is equal to 0 as well, so this is 0 plus 0, or basically equal to 0, over sine of 4 times 0, and sine of 0 is also equal to 0, so the result is 0 over 0, which is an indeterminate form. Now, we can manipulate this function to produce any value of a limit, or we can use the L'Hopital's rule to solve for this problem. Now, in using the L'Hopital's rule, we're just going to simply determine the derivative of this one and determine the derivative of the denominator independently with each other, and then we're going to evaluate the limit of the resulting expression or the resulting function as x approaches 0. Now, the derivative of x plus tangent of x with respect to x is equal to 1, alright? So the derivative of x is 1 plus the derivative of tangent of x with respect to x, that is equal to secant squared of x, all over the derivative of sine of 4 of x is cosine of 4 of x multiplied by 4. Now, if we're going to determine the limit of this one as x approaches 0, this is now equal to 1 plus secant of 0, or secant is actually equal to 1 over cosine squared of 0 all over cosine of 4x, that is 4 multiplied by cosine of 4 times 0. So evaluating this one, we have 1 plus 1 over cosine squared of 0 is equal to 1 over 1, so this is basically equal to 1, all over 4 multiplied by cosine of 4 of 0, and this is cosine of 0, and cosine of 0 is also equal to 1, so that's equal to 4. And simplifying this one, we now have 2 over 4, or this is equal to 1/2. For the second example, we have in here limit of beta all over arc sine of beta as beta approaches 0. So if we're going to evaluate this one, we have 0 over arc sine of beta is also equal to 0, so this is an indeterminate form. And we can use the L'Hopital's rule to solve for the limit of this function as beta approaches 0. To do that, we're going to take the derivative of the numerator with respect to beta. So the derivative of beta with respect to beta is equal to 1 all over the derivative of arcsine of beta. Alright, so if we're going to recall, the formula for the derivative with respect to x of arcsine of u, this is equal to du over dx all over the square root of 1 minus u squared. And our u in this arcsine is beta, so the derivative of beta with respect to beta is equal to 1 all over the square root of 1 minus beta squared. Now, if we're going to simplify this one, this is equal to the square root of 1 minus beta squared all over 1, or simply square root of 1 minus beta squared, and evaluating the resulting expression to the limit as beta approaches 0, then this is now equal to the square root of 1 minus 0 squared, or equal to 1. For the third problem here, we're going to evaluate the limit of y squared all over ln of cosine of y as y approaches 0. So if we're going to evaluate this one, this is now equal to 0 squared all over the natural logarithm of cosine of 0, and cosine of 0 is equal to 1. Or this is now equal to 0 over the natural logarithm of 1 is also equal to 0. So the answer is an indeterminate value if we're going to evaluate this one with as y approaches 0. And since the result is an indeterminate form, then we can use L'Hopital's rule to solve for this one. So this is now equal to the derivative of y squared, that is equal to 2y, all over the derivative of the natural logarithm of cosine y. So if we're going to recall, the derivative with respect to x of ln of u is equal to du over dx all over u. Applying that formula, the derivative of cosine of x or cosine of y with respect to y all over cosine of y. So this is now equal to 2y all over the derivative of cosine of y is negative sine of y over cosine of y. Now simplifying this one, we have negative 2y cosine of y all over sine of y. So this is now the derivative of, or this is now the simplification of the derivative of the numerator and the derivative of the denominator independently. Solving for the limit of this function as y approaches 0, this is now equal to 2 multiplied by 0 multiplied by cosine of 0 all over sine of 0. And the result to this one is still equal to 0 over 0, which is still an indeterminate form. Now, how are we going to manipulate this one in order for us to get a value of the limit of this function as y approaches 0? So what we can do in here is to multiply both numerator and the denominator with 1 over y. So if we're going to multiply numerator 2y cosine of y with 1 over y, and we're also going to multiply the denominator sine y with 1 over y, the resulting expression would now be 2 cosine of y all over sine of y over y. So let's not forget the negative sign in here. And if we're going to determine the limit of this function as y approaches 0, so the limit of 2 cosine of y as y approaches 0, so that's now equal to 2 multiplied by 1, all over the limit of sine of y as y approaches 0. If we're going to recall, the limit of sine of alpha over alpha as alpha approaches 0, this is theorem number 7, this is equal to 1. So if that's the case, then the limit of sine of y over y as y approaches 0 is also equal to 1. So the limit of the given function is equal to 1. For the fourth problem here, we have the limit of 1 plus cosine of 2 pi y all over 2y minus 1 quantity squared as y approaches 1/2. So if we're going to evaluate this one, this is now equal to 1 plus cosine of 2 pi multiplied by 1/2 all over 2 multiplied by 1/2 minus 1 quantity squared. So evaluating this one, this is now equal to 1 plus cosine of 2 pi multiplied by 1/2. So 2 will basically cancel out with 2, and cosine of pi is equal to negative 1. All over 2 multiplied by 1/2, so 2 will basically cancel out with 2 in there also, and 1 minus 1 is equal to 0 squared, so this is equal to 0 squared, or this is basically 0 over 0, which is an indeterminate form. Alright? So, since the result is 0 over 0, we can use the L'Hopital's rule to solve for the limit of this function as y approaches 1/2. And to do that, we're going to get the derivative of the numerator, and the derivative of the numerator is equal to negative sine of 2 pi times y multiplied by the derivative of 2 pi y, which is 2 pi. All over, the derivative of the denominator is equal to 2 multiplied by 2y minus 1 raised to 1 multiplied by 2, right? Because this is u raised to n, and the derivative of u raised to n with respect to x is equal to n u raised to n minus 1 du over dx. So if we're going to apply this one, that would now be 2. U is 2y minus 1, n minus 1 is equal to 1, so that's raised to 1, and the derivative of 2y minus 1 is equal to 2. So if we're just going to simplify this one, this is now negative 2 pi sine of 2 pi y all over 4y, alright? So 2 times 2 times 2y, so that is 8y, and then 2 times 2 times negative 1, so that is minus 4. Now, if we're going to evaluate the limit of this expression as y approaches 1/2, this is now equal to negative 2 pi sine of 2 pi multiplied by 1/2 all over 8 multiplied by 1/2 minus 4, and this is now equal to sine of 2 pi, so 2 in here will cancel out with 2, and sine of pi is equal to 0. So 0 times 2 pi, that's equal to 0. All over 8 over 2, so that's equal to 4, minus 4, that's still equal to 0. And the result is still an indeterminate form. Since the result is still an indeterminate form, we can still use L'Hopital's rule to solve for the limit of this function. And using the L'Hopital's rule, again, we're going to determine the derivative of this one and the derivative of this one independently, and then we're going to get the limit of the resulting expression as y approaches 1/2. So to do that, we now have the derivative of negative 2 pi, alright, so negative 2 pi is a constant. The derivative of sine of 2 pi y, that is equal to cosine of 2 pi y multiplied by the derivative of 2 pi y, which is equal to 2 pi. All over the derivative of 8y, that is equal to 8, and the derivative of 4, that's equal to 0. Now, getting the limit of this expression as y approaches 1/2, so this is now equal to negative 2 pi multiplied by 2 pi, so that is 4 pi squared multiplied by cosine of 2 pi multiplied by 1/2, right? All over 8. Now, 2 will cancel out here, so this is now equal to negative 4 pi squared cosine of pi is equal to -1 all over 8. This is now equal to, if we're going to simplify this one, 4 over 8, that is equal to 1/2. So this is basically 1/2 pi squared. So this is now the limit of this given expression as y approaches 1/2.